Welcome to another fabulous day in Calculus 3, and we are going to do the spherical coordinate system today, followed by triple integrals using spherical coordinates. So, fun times. It's really great. And the motivation for this is similar to the motivation every time we do a change of variables, and that is you might be trying to integrate a triple integral that just isn't integrable or not easily integrable in rectangular coordinates. So you want to convert everything. So that's the motivation. And for those of you who are going to take physics, in physics, when they do some things with, you'll see, vector fields, electromagnetic fields, they end up doing multiple integration. So double and triple integrals are important in the world of physics too, so you'll see. Okay, so of course, I got to have my meme with the pirates. R, yar, har. Which one is it? Okay, here is the spherical coordinate system. You're going to have an ordered triple. So the first coordinate is a distance. That's rho. Okay, so rho is a Greek letter. And it's kind of like a Greek letter for r. So it's going to be a directed distance, sort of like a radius, but not really. And it's sort of like the r in cylindrical coordinates with one big exception. The rho in spherical can never be negative, whereas when you're dealing with cylindrical or polar, r can be negative. Not my favorite, but it can. The second and third coordinates are angles. Okay? So similar to latitude, longitude when you're identifying points on the surface of Earth. So here's the official definition. You've got this ordered triple rho, comma, theta, comma, phi. So this is phi, also a Greek letter. Okay, some people pronounce it phi. I've heard different pronunciations. I'm going to pronounce it phi. Okay, so rho, theta, phi is your ordered triple. Rho is a distance. And it's the distance between your point and the origin. So it's always non-negative, greater than or equal to 0. Theta, good news about theta. Theta is the exact same theta angle that you learned from both polar and cylindrical. Okay? When your r is positive. And then phi is, it's an angle, but it's kind of a weird angle. It's going to be the angle between the positive z-axis and your line segment, OP. So here's a little diagram here. Let's say here's your point P right here. And if you draw a line segment connecting the point P to the origin, the angle that that line segment makes with the positive z-axis is phi. Now, phi cannot be any angle that you like. Theta can be positive, negative, or 0. Theta has all sorts of possibilities. Phi, not so much. Phi has to be in the range 0 to pi inclusive. Well, why is that? Well, if you're a point that lives on the positive z-axis, your phi is 0 because the angle you're making with the positive z-axis is 0. And then, you know, as you see here, this angle here looks like it might be something like 45 degrees or pi fourths. If you're a point here in the xy plane, what do you think your phi would be? Well, it's 90 degrees, which is pi halves. Okay. So what's the most that phi can be? Well, if you're a point down here on the negative z-axis, that's the maximum that phi can take on. So the maximum phi is pi, or 180 degrees. And that's if you're a point on top of the negative z-axis. Okay? So please note that both rho and phi can never go negative, both of those guys. Now, I want to say something about our physics brethren over there, because when you take a physics course and you're dealing with the spherical coordinate system, the physics people also use an ordered triple like us, but for some reason, they always put their phi second and their theta last. So don't get kind of flummoxed when you go to a physics class. Their phi is still the same phi that we're talking about, the angle between the point and the positive z-axis. And the theta is still the same theta. It's just that for some reason, when they give their ordered triple, they have it reversed. Okay, so I just want you to realize that. I had a student many years ago who took me for vector calculus and then went on to take physics, and she was emailing me going, hey, you know, in my physics class, this is going on. And I went, hey, don't worry, you're okay. They like to do it backwards. All right, let's talk about converting between spherical and rectangular or back. So if you already know your rho and your theta and your phi, and you need to get your x, y, and z, then these three equations are important. It's kind of hard to memorize these because they're pretty weird, you know, and that's why on your final, I'm going to let you create a formula and theorem sheet, 1 page. You're not allowed to put any worked out problems on that little formula sheet, and you'll be turning it in. Okay. Theorems and definitions and formulas only. So x is rho sine phi cos theta. Y is rho sine phi sine theta. Now notice both of those have something in common. Both the x and the y have a rho sine phi. So that's the only thing they have in common. And z is different altogether. Z is rho cos phi. Now, if you want to switch from rectangular to spherical, and you already know your x, y, and z, then rho squared is equal to x squared plus y squared plus z squared, which is equivalent essentially to rho being the same as the square root of x squared plus y squared plus z squared. So if I were you, I would know both of these. And then your tan theta is y over x, same as polar, and then the same as cylindrical coordinates. And then phi is rather annoying here. It's arc cos, the quotient z divided by the square root of x squared plus y squared plus z squared. And notice this square root of x squared plus y squared plus z squared is the same as rho. Now, what if you needed to go between spherical and cylindrical? Cylindrical is the new coordinate system we learned last time. Sometimes you might need to go back and forth between those coordinate systems, and these are the formulas to help you convert between cylindrical and spherical. Okay, let's do some converting of points now. Just convert points. We're just going to use some of these conversion formulas we just looked at. If you're going to convert a spherical point to rectangular, knowing that this ordered triple is rho, theta, and phi in that order, then you're going to use the formulas. X is rho sine phi cos theta. So it's going to be 8 sine pi fourths cos 7 pi 6. Uh-oh. Got to know a lot of trig formulas here, your trig stuff. So what the heck here? Sine of pi fourths is square root of 2 over 2. Cosine of 7 pi 6 is negative square root of 3 halves. Multiply these three together and reduce. I get negative 2 square root of 6. Save that for later. Y is equal to rho sine phi sine theta. So you're going to have 8 sine of pi fourths sine 7 pi 6. So that's going to be 8 times square root of 2 over 2 times negative a half. Multiply and reduce. I get negative 2 square root of 2. And finally, z is rho cos phi. So that's 8 cos pi fourths. So that's 8 times square root of 2 over 2 and reduce. You'll get 4 square root of 2. So your final answer is an ordered triple with -2 square root of 6 for your x coordinate, -2 square root of 2 for your y, and 4 square root of 2 for z. And there you're done. Example 20, convert the rectangular point given here to spherical coordinates. And you're just going to use your formulas now. This is rectangular, so it's understood that you've got x, y, and z in that order given to you. So you need to go get the rho and the theta and the phi. Okay, rho is the square root of x squared plus y squared plus z squared. So that's going to be the square root of square root of 3 squared plus 1 squared plus 2 square root of 3 squared. So it looks like we're going to have the square root of 3 plus 1 plus 12. But that's square root of 16, which gives 4. Nice. Theta is tan inverse y over x. So for us, that's tan inverse 1 over square root of 3. And if you use your graphing calculator in degrees mode, you'll get 30 degrees, and then you can convert that to radians, pi 6. And finally, phi is cos inverse of the quotient z all over square root of x squared plus y squared plus c squared, which is cos inverse of 2 square root of 3 all over this square root of x squared plus y squared plus z squared. But remember, we did that already, and that was 4. So after reducing, this is really cos inverse of square root of 3 halves. And of course, the range of cos inverse is 0 to pi. So we're hoping that that's going to be correct. And so this looks like it's going to be, I believe, pi 6. And so our final answer is the ordered triple 4, comma. Oh, wait, we're not done yet. Hold on. I didn't get my, no, I did 4. Sorry. I got both of them happen to be pi 6. That's not that common, but it's okay. So there's your final answer to example 20. So the next two examples are converting between cylindrical and spherical. So if you're going to do that, then you want to use these formulas up here to help you get between spherical and cylindrical. Okay. All right. So they want us to convert the spherical point to cylindrical. So that means that they gave us rho, theta, and phi, and we need r, theta, and z. Now, good news, this theta that you see in spherical is the same theta that you have in cylindrical. So you don't need to do anything there. Nice. So then how do you get your rho and your phi? So theta is just theta. So rho is going to be equal to the, or excuse me, we want r. R theta, so we want r squared is equal to rho squared sine squared phi, which is the same as r is equal to rho sine phi. So we're just going to use that formula. So that's going to be 18 sine pi thirds, and that looks like it's going to be 18 times square root of 3 halves, which reduces to 9 square root of 3. And then we just said that theta is equal to theta, so that's pi thirds. And then phi, or z rather, is dependent on phi because you need rho, cos, and phi. So if you look here, the z here is rho, cos, phi. So you're like, okay, 18 cosine pi thirds, and that's 18 times a half, which is 9. And so your final answer for this example is the ordered triple, weird, 9 square root of 3, comma, pi thirds, comma, 9. Here's your r, your theta, and your z. Okay, and we'll just go backwards now. We want to convert this r theta z, this cylindrical to spherical. So rho is equal to the square root of r squared plus z squared. So that's the square root of 2 squared plus -2 squared, but that's the square root of 4 plus 4, square root of 8, 2 root 2. Theta is just itself, 2 pi thirds. Phi is cos inverse of z all over rho, essentially. I mean, that's not what it says up here. Phi is equal to r cos z over square root of r squared plus z squared, but this is the same as rho. And I already got rho, so I'm just going to use it again. Very convenient. So this is cos inverse of -2 over 2 square root of 2. But after reducing, this is cos inverse of -1 over square root of 2, which is 3 pi fourths. So your final answer, your spherical coordinates, you got your rho, that's 2 square root of 2. Your theta is 2 pi thirds, and your phi is 3 pi fourths. And there's your final answer for that example, converting cylindrical to spherical. Okay, we're done converting points. Now let's do the more important work, which is, can you convert equations? So you'll be converting expressions in a triple integral. So this is more important than converting points. So why do we care about spherical? Well, I just mentioned the earlier motivation. You'll be into some triple integral, and it'll be easier if you convert to spherical. How do you know it's going to be easier to convert to spherical instead of, say, cylindrical? Because now we have 3 coordinate systems in 3D that we can do business with. So there's lots more choices, and you don't want to choose wrong. That can be dangerous. It turns out if you're dealing with a solid that has a point or a center of symmetry, like a sphere or a half plane or a cone, those are good candidates for converting to spherical. I want to tell you, though, I always convert to spherical if I'm dealing with a sphere as my region of integration I'm integrating over. Cones, well, you can convert to spherical, but it's a little bit more challenging than converting to cylindrical. So when I see a cone, I tend to convert to cylindrical. That's just my personal preference, but it lends itself to either. So let's do some converting equations now. All right, so let's convert to spherical from rectangular. So here's a very nice rectangular equation, happens to be a cone. How would you convert it to spherical? Well, you got to make the appropriate replacements because this one isn't so easy. I do want you to notice, let me just back up a little bit. This sphere, a sphere in spherical always has the equation, if it's centered at the origin, rho equals a constant. That's nice. Okay. So what do I mean by make appropriate replacements? Well, you got z squared. Well, z is rho cos phi. So you're going to have the left-hand side of that equation be rho squared cos squared. Or is that right? Oh, yeah. Then what? What's x squared plus y squared? Well, x is rho sine phi cos theta. So you're going to square it. And then y is rho sine phi sine theta. So you're going to square it. So this is a big mess. You could go, well, I'm done. I converted everything to spherical. Yeah, but you're probably not going to get much credit. Clean it up. Well, what do you mean clean it up? See if you can't solve it for something, you know, working on it. Usually you can try to solve it for rho, but that may not work either. So what can we do here? Clean this mess up. If you'll notice, these two terms on the right-hand side of the equals, both after squaring have a common factor of rho squared sine squared phi. So if I factor that out, the other factor will be cos squared plus sine squared, which is nice because the trig identity says that's just a 1. Okay, now what? I'm going to do something that's ordinarily illegal in math because I'm dividing by what could be potentially be 0, but we're going to assume that rho isn't 0, and that will allow us to do this. And then we've got a really weird equation. Cos squared phi equals sine squared phi. Clean it up more. Really? Yeah. Just try to go for it. Okay. So now what do you have? You have the equation 1 is equal to the quotient of sine squared divided by cos squared. But using a trig identity, sine over cos is tangent. So that's really tangent squared. Now I'm going to take the square root of both sides. Don't forget your plus or minus. And I'll have that tangent phi is plus or minus 1. And so if you take tan inverse of both sides, you'll have phi is tan inverse of plus or minus 1. So phi can either be pi fourths. Now, when you use your graphing calculator, arctan or tan inverse of -1 is negative pi fourths, but phi is not allowed to be a negative, as we discussed initially. Well, what do you do then? Well, you add pi to that, and you get phi is equal to 3 pi fourths. So what of it? So what is phi equals pi fourths? What does that surface look like? It turns out it's all the points whose angle that it's making with the positive z-axis is pi fourths. And it turns out to be an upper nap of a cone because all the points that live on this ice cream cone are pi fourths away from the positive z-axis. And then the 3 pi fourths, this is really cool. This is an angle of 3 pi fourths, all the points, and that turns out to be the lower nap of a cone. So those are cones. So together, we got one big old, the single equation represents what's known as a double napped cone. Both naps of the cone. You got an upwards facing ice cream cone and a downwards facing ice cream cone. Pretty cool. Letter B, they tell us it's a sphere, but okay. It's a sphere not centered at the origin, but how would you convert that to spherical coordinates? This one's not too hard. It's a lot easier because x squared plus y squared plus z squared, I mean, you could do those other formulas and you'd eventually factor everything out and you get rho squared. And then minus 4z, but z has the conversion rho cos phi, and you'd be done, but they usually like you to go a little extra. So we're going to go a little extra, and we're going to try and solve this for rho. And we're going to get rho is equal to 4 cos phi after reducing. And that's a sphere that is not centered at the origin. Ooh, really? Yeah. So I always like to really, let's check it out. This software is cool because when you type in rho, it gives it to you. No, it's not going to. How about R? Ah, there we go. Nice. So there it is. It is a sphere that is clearly not centered at the origin. Pretty cool, huh? Ooh, pretty. Nice. Lovely. I love it. What else? How about stripes? Oh, wow, that looks cool too. Very beautiful. Can't beat it, huh? All right. It's always fun. Yeah, it does look like a disco ball, doesn't it? All right, let's look at some set notation that describe different solids in space using spherical coordinates and try to see if we can't figure it out just by looking at it. Some of it's harder than others. You can, of course, go to a grapher and graph it. So check out the first set, rho theta phi, all the ordered triples, rho theta phi, where rho lies between 1 and 3. And what this is a solid points that lie between a sphere of radius 1 that's greater than a sphere of radius 1, but less than the sphere of radius 3. So these are all pictured on the next page. There it is. So this is where rho lies between 1 and 3. So the inside is hollow, and then you've got this sort of a shell, they call it. So that's kind of nice. And then this rho is equal to 2 cosecant phi. Oops, a little bit. Cosecant phi. That's the same as 2 times 1 over sine. And you can convert this, and it's going to end up looking like a cylindrical surface. And the rho 4 cos phi, well, we just saw what that looked like, right? That's going to look like that. It's a sphere not centered at the origin. And then this one, rho equals 2 cosecant phi, turns out to be a flat plane. Interesting. So planes are not the type of surfaces where I would convert to spherical coordinates, though. Yeah, no, not a good point. Okay, let's start triple integrals now. So you ready? You are now introduced, congratulations, to the spherical coordinate system. Yay! It's just another way to describe 3D, that's all, and to locate points in space. But instead of your ordered triple XYZ, you've got an ordered triple rho theta phi. So what about triple integrals? So you got to be careful here. So let's do a little bit of review. The volume element, which is denoted dV, when you're working with rectangular coordinates, is given by dz, dy, dx. That's one possibility. Of course, there's 5 others that I want to get into now, different order. You could have dy, dz, dx, and so on and so forth. But the main point is that they're just combinations of dz, dy, dx. That's the volume element for rectangular. What about the volume element for cylindrical? Now be careful because you got to be a pirate, right? So you're going to have r dz, dr, d theta. R dz, dr, d theta is the volume element for cylindrical coordinates. Now, the volume element for spherical, you're probably not going to believe me. It is, don't blow this on exams or quizzes, okay? Because if you do, I don't give partial credit because you have easy access to this. It's rho squared times sine phi times d rho d phi d theta, and typically in that order. Rarely do they mess up the order for you on that. And if you're asked to set up a triple integral in spherical coordinates, if I were you, I would choose this order. It's just common. And for polar and cylindrical, typically dr d theta is the order chosen, not d theta dr. Well, how come? Because traditionally they give you your r as a function of theta. So when you have functions of theta, then theta is going to be going from a pure number to a pure number. So logically, that would be the outer integral. Okay. True or false? This is a little tricky for a couple reasons. You know, just one reason is you're brand new to spherical coordinates with triple integrals. So you may have tough time eyeballing quickly where there may be an error when you haven't had any practice yet. But let's say you're trying to set up a triple integral representing the mass of an upper hemisphere centered at the origin of radius square root of 5. So if I were to draw the solid that they're integrating over for this triple integral, I'm just going to try to draw a northern hemisphere, if you will, that upper hemisphere, where the radius is square root of 5. Okay, I'm not very good at drawing, but you can hopefully use your imagination. That is an upper hemisphere. Okay, so there's the region of integration. They're giving us a density function. That's good, because when you're given the problem, find a mass, you need a density function, and they always put the density function in the integrand, and they did, and that's good. Okay, and what else? Well, this right here is correct. This is okay, because that is the correct volume element for spherical. Rho squared sine phi d rho d phi d theta. That's good. So is there something up with the limits? Let's check. For this upper hemisphere, you do have rho going from 0 to square root of 5. So for the innermost integral, the limits are good. So that's okay. Now, phi, they're saying, goes from negative pi halves to positive pi halves. Is that even legal?
No, it only goes from 0 to pi, right?
Right. This is not correct. Very good. Very good. Yeah, you can't have your phi ever go negative. Oh, dear. Now, the theta, I claim, is correct. Because if you look at what's going on in the xy plane, in other words, the projection of this hemisphere onto the xy plane, you'll get a circle centered at the origin of radius square root of 5. And then it does look like theta is going all the way around between 0 and 2 pi. So it looks like the phi is not so good. So the answer here is going to be false, because they have the incorrect limits for phi. Now, what if we were going to fix it? Let's fix it so that it would be good. So what would be the correct limits for phi here? Now, please, I know it's early and you're probably tired, but if you really get what I'm about to do here, your spherical coordinates homework and exams will be much sweeter. So what are those limits for phi? Let's take a look at this region of integration. I claim that, now remember, the phi is angles that the solid makes between the positive z-axis, which is right here, you know, and any points that live on the positive z-axis have a phi of 0. And since there are some points here of this upper hemisphere that are exactly coinciding with the z-axis, our lowest limit for phi will be 0. Now what? Well, you keep going out, keep going out. It looks like the most that phi is ever going to get, since this is the upper hemisphere, the largest value for phi here will be 90 degrees, or pi halves. Okay? So the phi for this problem, if they had put the range being from 0 to pi halves here, that would have been good. So if we can change this lower limit to 0, it would have been perfect. And that concludes that example. So just a little rhetorical question. What if they had, in this problem, example 25, instead of the upper hemisphere, what if they said, no, we don't want the hemisphere, we want the whole entire sphere? Just pretend that was the original problem. It isn't, but what if they wanted the whole entire sphere? So then, you know, you'd have a whole ball here centered at the origin of radius square root of 5. what would phi, by the way, all the limits would be the same. The only limit that would change would be phi. So I claim the lower limit would still be a 0, but the upper limit would be
Pi.
pi. Very good. If it were the entire sphere, we were trying to find the mass. And that's important for you to know. And if you got that, you're halfway there. Okay, now this is just a penumbra of a proof. Penumbra meaning sort of a very, like a hand waving proof. I'm not going to go through the whole thing. But if you do the partition of a sector, if you will, a spherical sector, and you partitioned it into little itty bitty spherical sectors, you'd get and looked at a single one of these spherical sectors. This is not a rectangular box right there. I mean, it looks kind of like, it's kind of curvy, it's got like that. It's kind of a block, but not really. It kind of grows outward as you get further away from the origin of the sphere. And if you look and did some geometry on that, the volume of that block would be rho squared sine phi, delta rho, delta phi, delta theta. And then you do the whole partition thing, and you take Riemann sums, and so on. So what would happen is your volume element would turn into what I already told you what it is. It's rho squared sine phi d rho d phi d theta. And if you did have an integrand here, you would need to convert it to spherical also by using all of the conversion formulas for x, y, and z. And then hopefully you can integrate in spherical coordinates. Yay! So let's do some triple integrals. So most of the time, you're going to be given a rectangular coordinates triple integral that is easier to integrate if you can convert to spherical. Very rarely do you go the reverse, okay? Still got to know all your conversion formulas, though. You'll see. So let's take a look at our very first triple integral. Here it is. And they want us to use spherical coordinates. And the solid named big Q is the entire sphere given by x squared plus y squared plus z squared equals 25. Well, folks, this is a sphere centered at the origin of radius 5, and it's the entire sphere, like this. Okay, nice. So all of the limits for rho, theta, and phi will be constants. So rho is going to bloom out from the origin and, all the way out up to the 5. As we discussed, the phi is going to go the full range for phi. Phi is going to, remember, 0 starts at the positive z-axis, is going to go the full range. So there's your phi. So it's going to go between 0 and pi. Now, what's theta doing? If you look at what the sphere is doing in the xy plane, and you can also do this by setting z equal to 0 to see what's going on, the trace it makes in the xy plane, and you'll get the equation x squared plus y squared equals 25, and the trace is just a circle centered at the origin of radius 5. So what's theta doing? Well, theta is just going the full revolution, 0 to 2 pi. Yay! So when we convert this triple integral to spherical coordinates, we now know the range or limits for all of the variables. So the dv is rho squared sine phi d rho d phi d theta. Theta is 0 to 2 pi. The middle integral is phi, that's 0 to pi. And rho is 0 to 5. Now the question is, what about this integrand? The 1 over x squared plus y squared plus z squared. How do we rewrite that using spherical? Well, you could put in all of those horrible conversion formulas for x, y, and z, But if you remember that x squared plus y squared plus z squared is rho squared, after you do all your factoring and trig identities, that's what will happen. And now you can continue. And these rho squareds cancel. Does that always happen? No. But if it does, it's like, sweet. Okay. Now let's integrate sine phi with respect to rho. Well, sine phi is just a constant multiple when you're integrating with respect to rho. So you're just going to have sine phi times rho, where rho is going to be evaluated between 0 and 5. That's just going to be 5. And so I'm going to pull the 5 out. Now you're going to integrate sine phi with respect to phi. Now remember that the integral of sine is negative cos. So be real careful there. Negative cos phi. And that's going to get evaluated between the limits of phi, which are 0 and pi. And be careful, because this can be a place where you make a silly mistake. And now you got a lot of negatives floating around. Also very dangerous, you know. Miss that one negative and then the whole thing is bad. So it turns out that cosine pi is -1, but you have a negative in front of it. So -1 is, and then here you have a minus and a minus, so that's a plus. And then cosine 0 is 1. So really here you have 1 plus 1. That's like above my pay grade. And that's a 2. We're going to pull it out in front. And last but not least, you're just asked to evaluate essentially a 1 with respect to theta. And that's just going to be a theta. And the limits are 0 to 2 pi. So 20 pi is the final answer for this example. Yeah, not too bad, right? Okay, let's do one that's a little bit trickier. Started off easy for a reason. I know. Yeah, we got some more. So we're going to use a triple integral in spherical coordinates to find the mass of a solid now that's inside a sphere given by x squared plus y squared plus z squared equals 9. That's just centered at the origin of radius 3. Yeah. But outside the sphere x squared plus y squared plus z squared equals 1. And that's a sphere centered at the origin of radius 1. So it's going to turn out that your rho lies between 1 and 3. This is important. It's one of those spherical shells. Phi is going to do the whole thing because you're talking about full-on spheres centered at the origin. So it's going to do its full range 0 to pi. And when either of those spheres cuts into the xy plane, your xy plane is going to look like 2 concentric circles, one of radius 1, the other of radius 3. So your theta, which you already know and love, is going to be doing a full revolution, 0 to 2 pi. Okay, so your mass is going to be a triple integral with the density function as the integrand, which they didn't give to us. Aha! And that's going to make this a little tricky, so watch closely. And then it's going to be over this solid, we'll call it Q, and then we have a volume element, dV. This is just sort of a generic looking triple integral, and this is how you denote it. Your region of integration we're calling Q, and that's underneath these 3 integral symbols. Okay? So what is this, and how do we find it? So we're going to have to do some work. They gave you some information about it. They said that the density at any point is directly proportional to the distance from the origin. So this fxyz, this density is going to be some constant of proportionality times the distance to the origin. But what is that? I mean, if you're in 3D, And you're a point P, let's say you're a point P in this, on this Q region here with coordinates X, Y, Z. What's the distance between X, Y, Z and the origin? Well, you know from your distance in 3D that we did like the very first week of class, the square root of the sum of the squares of the differences between the X, Y, and Z coordinates. And this is just going to be the square root of X squared plus Y squared plus Z squared. So what are we really saying right now? We're saying that the fxyz is going to be equal to some constant of proportionality, just write it down, times your distance, but that's the square root of X squared plus Y squared plus Z squared. So the mass is going to look like this now. This is what we have so far. And now you're ready for conversion. So here we go. And I'm going to pull the K out front. That'll be in our final answer. We don't know what that is. It's just some multiple. It's constant of proportionality. And remember, the volume element for spherical is rho squared times sine phi d rho d phi d theta. D rho d phi d theta. The square root of X squared plus Y squared plus Z squared is simply rho. And remember, we agreed that rho is going to go from 1 to 3, phi was going to go from 0 to pi, and theta was going to go from 0 to 2 pi. So there, I set up my triple integral representing the mass. And now let's continue. First up, combine all your powers of rho into a single power of rho, so you don't forget. And now when I integrate rho cubed with respect to rho, I'm just going to keep copying down the sine phi here. That's going to be rho to the 4th, divide out by 4. And remember, the limits for rho are 1 to 3. So be careful. It's kind of weird. So you're having 3 to the 4th over 4 minus 1 to the 4th over 4. I know, what the heck is that? 81 fourths minus 1/4. That's not too bad. It's 80 fourths, which reduces to 20. So that's just a multiple. So I'm going to pull the multiple of 20 out in front, and then I only have a double integral left. And remember, the integral, oops, that 20k is not in front of an equals, sorry, 20k. So we're equaling this. And then the integral of sine phi, remember, is minus cos. Be careful, it's minus cos. And you're going to evaluate between those limits, 0 and pi. And we once again have the minus cos pi minus a minus cos 0. Oh, not that again. Minus minus 1 plus 1. So this is 1 plus 1, which is 2. And so if you pull your 2 out in front, you're now going to integrate 1 with respect to theta. You've got a 40k here. You're going to get theta going between 0 and 2 pi. So what's 40k times 2 pi? I get final answer 80 pi k. K is just a constant of proportionality for that density function. So the mass is 80 pi k. Woo! That was nuts. 80 pi k is your mass. Okay, so far it's not been too bad. The recap on that was the density function was a little bit tricky because they didn't hand it to us. A lot of times they just hand you a nice density function, and they weren't too nice about that. Okay, example 28 says rewrite but don't evaluate the triple integral. This is just to see if you know what the region of integration is. That's the tricky part. So when you're looking at x and it's going between -8 and +8, so you would draw those vertical lines. And then what's y doing? Y is going between negative, y equals negative square root of 64 minus x squared. That's the lower semicircle of a circle centered at the origin of radius 8. And then y equals positive square root of 64 minus x squared. That's the upper semicircle. So it looks like this is the region in the xy plane, but then hold on a minute. If z is equal, the upper limit for z is that, and I claim that's an upper hemisphere of a sphere centered at the origin of radius 8, and z equals negative square root of 64 minus x squared. That is the lower hemisphere. So together with the lower and the upper, you have a full-on sphere. So I claim the region of integration is a full-blown sphere centered at the origin of radius 8, based on all the limits of these integrals. Okay, so the region is a sphere centered at the origin of radius 8. Well, how does that help? Well, if you were asked to convert this to spherical, then your rho is going from 0 to 8, your theta is going from, or excuse me, your phi is going from 0 to pi, and your theta is doing the full revolution here in the xy plane, 0 to 2 pi. And then your volume element, of course, is going to be rho squared sine phi d rho d phi d theta. You just have to worry about how are you going to convert this integram, which looks like a hot mess. Well, you could do all the appropriate conversion formulas, but I want you to notice something. Do you notice that z is a common factor? If I factor out a z from all three of those terms, the other factor is going to be x squared plus y squared plus z squared. Yeah, so what? Well, you could replace z with rho cos phi, because that's what he is. And then x squared plus y squared plus z squared is simply rho squared. So now if you had to, you could, you know, basically do this integration. I'm not going to, they didn't ask us. I would first combine all of your powers of rho into a single power of rho before you begin. And that looks like it would be rho to the 5th. And this wouldn't be too hard to do. We'll do something similar to it, but not yet. We hope. Well, maybe I should say something about this. If you had to evaluate this integral, well, integrating with respect to rho is pretty easy because the antiderivative of rho to the 5th is rho to the 6 over 6. And you would evaluate that between the limits of 0 and 8. Now, keep in mind, you still have a cos phi times a sine phi in there. And then you also have d phi d theta. And then what the heck is 8 to the 6th power? Oh, God. I don't know. Oh, man. 8 to the 6th is 262,144. Yeah, I knew that. Does it divide by 6 nicely? No, it doesn't. Well, we'll just, if we pull that multiple out, I don't feel like reducing this fraction right now. I want to make a point. Cos phi, sine phi, because you're going to have something like this on your exam this coming week. Oh yeah, I'm not making this up, so I want to make sure you get it. How would you integrate this? There's a couple ways to do it. Let me show you the way that I prefer you do it. You could use a double angle formula backwards. I don't want you to. I'm going to use u substitution with the power rule. If I let u be sine phi, then du is cos phi, d phi. So this integral here actually looks like the integral of u du. Nice, because the antiderivative is u squared over 2. Nice. So what does that mean? Sine squared phi over 2, and you're evaluating that between the limits here of 0 and pi, and that would go to 0. So that would not be fun. Well, hopefully that wouldn't be the case. They wouldn't evaluate it from 0 to pi. But I wanted to show you the u sub. Okay. Next up, example 29. This is the kind of stuff that I like putting on my final. Hint, hint. Yeah. This kind of integration too. What do you mean? You'll see. one of my personal favorites. First, yeah, you definitely want to convert this to spherical. What's the region of integration though? It looks like x is going between 0 and 5 only. Y is going between 0 and the upper semicircle. And so it looks like you're staying in the first quadrant for the region if you're looking at the trace it's making in the xy plane. And z is going between z equals 0 and z equals the square root of 25 minus x squared minus y squared. And this tells us it's an upper hemisphere centered at the origin of radius 5. So that means that rho is going to go between 0 and 5. And then phi, since you're doing a hemisphere only, it's going to go between 0 and pi halves. And then because you're only doing a quarter of a circle, that means your theta is going to be between 0 and pi halves also. So now what? Well, now you got to convert. You're going to go boom, boom, boom. And if I were you, I'd go, rho squared sine phi d rho d phi d theta. Put your volume element always in there. Now, how do you convert the integral they gave us? Now, remember, the integral was 1 over 1 plus x squared plus y squared plus z squared. So how do you convert that to spherical coordinates? Well, it's 1 over 1 plus, and the sum of x squared plus y squared plus z squared is rho squared. And then you had your rho was 0 to 5, phi was 0 to pi halves, and theta was 0 to pi halves. Okay, now how do you integrate this? This is what a little bit tricky, because you really have the integral of rho squared over 1 plus rho squared d rho. And this is what's known as an improper rational function. And I did something similar when we were discussing polar coordinates a couple lectures ago. So you have to do polynomial long division. Oh yeah. So how many times does the denominator go into the numerator? Look at the high power terms only. Rho squared goes into rho squared how many times? Once. Multiply the quotient by the divisor and then subtract. I get a -1 for the remainder. This is the divisor, and this is the quotient. Okay, so then how do you rewrite this? I go, I did my polynomial long division, now what? I'm stuck. So you always write it as quotient plus remainder over divisor. So your integral is going to look like 1 plus the -1 over rho squared plus 1. So now I claim that you can integrate this with respect to rho. Well, the antiderivative of 1 with respect to rho is rho. I hope you can see that this is arctan. And maybe I should write it as arctan. Arctan of 1. Or arctan of rho, rather, rho over 1. And you're going to evaluate this between the limits of 0 and 5. Now, this is going to be kind of a yucky number, because when you plug in your limits, you're just simply going to get 5 plus arctan of 5. And arctan of 5 is some funky number, just leave it. So then what? At this point in time, I'm going to pull this multiple out. You've got a double integral, sine phi d theta, and the antiderivative of sine phi. We've already done this a few times now, so it's getting a little old, minus cos, but you're going to go between 0 and pi halves. I'm continuing to write this weird number down, which is 5 plus arctan of 5. Just some weird number. And cosine of pi halves is 0. Minus is a plus 1. So that doesn't contribute anything. And then when you integrate 1 with respect to theta, you're just going to get 2 pi. And then your final answer is going to be this weird number, 5 plus arctan of 5, whatever that is, times pi halves. Woo! And we're done with that example. Pretty funny. So to recap this, the hard part of this problem was, again, trying to figure out what your region of integration is based on all the limits of the triple integral. Like, what is that? Is it a sphere, a portion of a sphere? What is it? Because if you don't know, then you won't be able to convert. You've got to figure it out. Is it a quarter of a circle or a sphere? Maybe it's an entire sphere or half a sphere. That can get a little bit dangerous. And then, of course, polynomial long division and arctan rule. It's like a triple whammy. I love those. It's all good. So now let's take a look at example 30. This is involving the cone. Remember, I told you I'm not a really big fan of cones for spherical. But here they're asking us to find the volume of a solid bounded above by a sphere and below by a cone. So this is a little tricky to even visualize the solid. So it's, the cone is actually a double napped cone, but we don't want the whole double nap cone. How do I know? Because they want us to have it bounded below by the cone. And now the sphere that it's bounded above by, this is a sphere of, radius 3. You got the whole sphere. Oh, that's a terrible looking sphere. Oh my goodness, that's sad. But we don't even want this whole sphere. We want, the sphere right here where it's going to make the cone look like it's got a scoop of ice cream in it. So the solid is actually looking like an ice cream cone. Yeah, where the upper capping surface is the sphere and the bottom of the solid, if you will, the underbelly is the cone. Pretty nice looking solid. So we want to find the volume of it. Nice. So the hard part about this problem, there's a couple of hard parts about this problem. I don't like it, but you need to figure out the projection of this solid onto the XY plane. And the fattest portion is right where those two equations have their intersection. That's where the fattest portion. So the intersection of the surfaces, and you can do this by setting z equal to z. Now, what's going to be easier though is if you set z squared equal to z squared. It'll be easier to do it that way because the cone is already given as a z squared. Yeah. And then if you solve this, the sphere equation for z squared, you'll get 9 minus x squared minus y squared. So solve this. And then if you add x squared and y squared to both sides of the equation, and then divide both sides by 2, you're going to get a circle centered at the origin of radius, kind of a weird radius, square root of 9/2, which is 3 over square root of 2. Yeah, but that's it, okay? So that would be this projection right here. A circle, this is right here, this circle centered at the origin. That's the projection. Oh boy. So this circle here is the projection of the solid onto the XY plane. And you need that because that helps you figure out what theta is doing. And I hope you can tell that since you're making a full revolution, that tells us that our theta is going to be going between 0 and 2 pi. Nice. So now the hard part is going to be what is rho doing and what is going to be what phi is doing. Phi is really going to be the problem. Yeah. Now I claim that rho is going between 0 and 3 because the biggest it gets here is this 3 and it kind of blows out. Remember I told you it kind of blooms. You got that. But the question is, what the heck is phi doing? And this one's not easy. So this is the part that's like, oh man. So how do you get it? So first, I'm going to do this kind of slowly so you can kind of see where this logic is. So we got x squared plus y squared plus z squared equals 9. But then we know that x squared plus y squared, but based on the cone, okay, right here, that's z squared also. So really what we have is z squared plus z squared is equal to 9. Anytime I use my erase tool, it gets a little unhappy. Okay. So we have z squared plus z squared equals 9, which tells us 2z squared equals 9, which tells us z squared is equal to 9 halves. Okay, but then if you take the square root of both sides, you get z is equal to plus or minus 3 over square root of 2. Okay, but here's the weird part. Z is equal to rho cos phi. You know this. So if I substitute in this equation here, I'm going to pick the positive because where z isn't negative on our solid. So we really have that z is equal to, no, I don't want to do that. Wow. But we know that rho is 3. So what we're saying is z is equal to positive 3 over square root of 2. But z is also equal to 3 cos phi. So we have 3 cos phi is equal to 3 over square root of 2. If we divide out by 3, we get that cosine phi is 1 over square root of 2. And you may be going, why am I doing all this? Because remember, we're trying to find out the limits on phi. And if you look at cos inverse of 1 over square root of 2, and I'll have you know that if you multiply 1 over square root of 2 by square root of 2 over square root of 2, it's the same as square root of 2 over 2. And this ends up being pi fourths. And in fact, that is the maximum that this cone gives when you talk about the angle it's making with the positive z axis. So good news, we now have that phi goes between 0 and pi fourths for this region. So now if we're trying to find the volume of this thing, we're going to go, the volume is the triple integral of, and when you're doing volume, you just have 1 as the integrand. The volume element for spherical is rho squared sine phi d rho d phi d theta. Rho is going between 0 and 3. Phi is going between 0 and pi fourths. And theta is going between 0 and 2 pi. Okay, now this is a pretty easy integral to do, so I'll let you finish it out. Make sure you check your answer, though. It is kind of a weird number. It's 9 pi times the quantity 2 minus square root of 2. I know, cubic units. Oh my goodness, are you kidding me? No, and that is a positive number. The approximate answer is 16.56 cubic units. And that is a positive answer. That's the volume of an ice cream cone, or this ice cream cone anyway. Pretty cool. Now, what if somebody said, hey, I want you to set up a triple integral that represents the volume of a sphere, x squared plus y squared plus z squared equals 100. Now, folks, there's no reason why you should use a triple integral to find the volume of a sphere. I mean, that's overkill. Well, how come? Because the volume of a sphere has a very nice formula, 4/3 pi r cubed. So you probably wouldn't use a triple integral to find the volume of a sphere because you already know. But a lot of times you're integrating over a solid that might be a sphere given by that equation, where the integrand would be something other than a 1. So you should know at least how to set up a triple integral representing the volume of something that's easy to find with a straight formula. So I'm going to put you in breakout rooms and have you try this one on your own. Right. So what could it be? So your volume has to look like, you know, triple 1 dV over the region. Well, none of those look like a 1. Well, that's good because there really is a 1 there, but the dV is rho squared sine phi d rho d phi d theta. And all of the choices for this multiple choice problem look like they have the correct volume element there. So then what? Well, then you have to figure out the limits. Now, if you are doing the entire sphere, then your rho would be between 0 and 10, because this equation here is an entire sphere centered at the origin of radius 10. Oops, centered. Can't write too fast this morning. Radius 10. So that would mean rho goes from 0 to 10. So that's easy. And then the phi would be 0. That's supposed to be a 10. The phi, since it's the entire sphere centered at the origin, phi would do its entire range, 0 to pi. And then theta would do its whole, revolution, 0 to 2 pi. But it doesn't look like any of the choices look like this. This would be legal, though. You could do this, and this would be one of the right answers. But that's not one of the choices. Uh-oh. Well, I think what they're using is symmetry. Because if you look at a sphere centered at the origin, and remember, there's 8 octants when you're in 3D. And it looks like every single one of these things is getting multiplied by an 8. Oh, so they're only taking the portion of the sphere that's in the first octant, which would look like this. That's not a very good cut of the sphere, okay? It'd be an eighth of a sphere. And that way we would multiply by 8. Okay, but then what? You'd still have your rho going from 0 to 10, okay? That's true. And then, since you're only looking at the portion of the sphere that's above the xy plane, your phi would be going from 0 to pi halves. And since you're only looking at the part in the first octant, that means you'd only be in the first quadrant in the xy plane. So that means that you would have your theta going between 0 and pi halves, and then you would multiply by 8. Now, it looks like the choice letter B is perfect. That works. Did anybody get choice B? I hope.
Yeah.
Okay, good. But I claim there's one more choice here that actually is legit. It wouldn't be the one that I would use, but it's the portion of the sphere not in the first octant, but it's where theta would be going between 0 and 2 pi. So it'd sort of be in the back there. So that would be that eighth of a sphere, and that would also be okay. Okay, so it turns out letter E would also be legit. The other ones are not okay at all. Okay. So here's a really cool exam problem that I got from the net. I was just rooting around. I found this on some other instructor's exams, kind of fun. And I thought, wow, that's cool. So it's multiple choice. Convert the following integral from spherical to rectangular. Now, usually you're never asked to do this. This is sort of going backwards. Like, why would I want to go from spherical to rectangular? Usually you don't. But if you understand this whole process of converting from rectangular to spherical, then that means this is not that hard for you. You really understand it. So what would be the correct thing here? Now, if you look at the d rho d phi d theta, and they're actually doing d theta d phi. Oh, that's kind of weird. All right, fine. So it looks like their phi is doing the full range of what phi is allowed to do, 0 to pi. Okay. And it looks like theta is going between 0 and 2 pi, so it's doing its full revolution. And rho is going between 0 and 2. So this looks like the region is a complete entire sphere centered at the origin of radius 2. Okay, so that's helpful because then when we do our dz, dy, dx or whatever, you can kind of figure that out. So it looks like all the choices are dx, dy, dz. Not my personal favorite, but still you can do it. Z is going from -2 to 2, Y is going from the lower half of a semicircle to the upper half, and X is going from the bottom hemisphere to an upper hemisphere. So those look good there. And then the question, but this one is doing the same thing. So is that one correct? You have to be careful because you have to notice that this rho squared sine phi, when you convert to rectangular, disappears. Like you don't try to convert rho squared sine phi to rectangular. That's part of the volume element for spherical. So this x squared plus y squared plus z squared, no. So letter A is definitely not one of the possibilities. Now, what about this integrand? 2 to the 1 plus square root of x squared plus y squared plus z squared. Does that look like 2 to the rho plus 1? Yes. This is okay. So it turns out the only choice that works for the region of integration as well as for the integrand is letter B. So letter B would be the correct choice for the rectangular coordinates for that particular problem. Now let's finish off with a couple of average value problems. I'm just going to basically do the setup and I'll let you finish them out. When you're doing average value in triple integrals, remember that average value of a function, sometimes you'll call it f bar, some textbooks say f subscript average, is 1 over, in this case, it'd be the volume of the solid that you're integrating over. And then you have your triple integral over that solid. And then you put your function that you're trying to find the average value of in the integrand itself. Okay. And they're giving the average value to you and they want cylindrical coordinates. So you're going to go, all right, F average is, and then you'll go like this, you go R, and then the volume element for cylindrical is R dz dr d theta. And of course, you'd want to multiply these powers of R into a single power of R. Now, what about the region of integration? The region of integration is a, whoop, it's a cylinder of radius 1 where Z goes between a high of 1, like a flat plane is capping it, and the lower limit is the plane Z equals -1. So that would be the limits for the Z innermost integral. R would go from 0 to 1. And in the xy plane, it looks like theta is going from 0 to 2 pi. And then you'd have 1 over the volume of your cylinder. Now, volume of a cylinder is actually a nice formula. That would be pi r squared h. Now, if you look at this cylinder, what is the height? What is the height h? The
2.
height is 2. Yeah, it's 1 minus a -1. So our height would be 2. And they already told us the radius of the cylinder is 1. So r squared is 1 squared pi. So there's your volume of your cylinder. It's 2 pi cubic units. Okay? So you'd have 1 over 2 pi. And then you would do this integral here. And then you'd finish it out. I think you can finish it out. I'll just put etc. Your final answer is 2/3. Okay? If you do everything, it's an easy triple integral to do. Now, what about spherical coordinates? So you're still going to have 1 over the volume of your solid. And, you know, triple, triple, triple. Put your F here, whatever it is that you're trying to find the average value of, and then your volume element. Okay, they're giving you a solid ball is the solid. So you're going to use 4/3 pi r cubed to get the volume of a solid. So 4/3 pi 1 cubed, because they gave you the radius. And so this is going to be 1 divided by 4/3 pi times this triple integral. And the solid ball is going to have rho go from 0 to 1. P will do the whole range since it's a full ball centered at the origin, 0 to pi. And then theta will do a full revolution, 0 to 2 pi. You're going to put your function you're trying to find the average value of right there in the integrand. And then your volume element is rho squared sine phi d rho d phi d theta. Please remember to multiply your powers of rho into a single power of rho before you do the integration. Your final answer here is going to be 3/4. Okay, if you do everything correctly. All right, average value. And finally, what if you are asked to find the average value over a surface, which I think you were asked to do in the section for surface area in the homework. So it's kind of hard. In fact, I think this was the problem. I stole this from my lab math, and the numbers might be changed to protect the innocent there. Yeah. So how do we do that? So the cone is a cone. It's a double napped cone, but then they're telling you, oh, they only want the portion of the cone between z equals 0 and z equals 2. So it's capped above by the plane, z equals 2. So the volume of a cone, and actually you want area, surface area of a cone. Surface area of a cone. You need this. Why? Because your F average over surface area is going to be 1 over the surface area of the surface that you're trying to find the average value of times a double integral, and it's a surface integral like this. Oh, oops, right now. Wrong thing. This is a little bit tricky. So you're going to put your function you're trying to find your average value of. So this is kind of a hard problem. I'm not going to put something this hard on the midterm, okay? Don't even think about it. But I do want to say that let's do this first. This is kind of hard because you're going to actually have to do a surface integral for that first. So the surface integral of the cone is going to use the surface area formula, and you will have one of these on your midterm. Oh, yeah. So if your cone is given by z squared equals x squared plus y squared, if I were you, I'd first solve for z. And that's your f right there. And when you see the f's here, you're going to go get your fx. And then, of course, you're going to use your chain rule. This is not pretty. And I'm going to reduce this to lowest terms and then put the radical back in. Now, one thing you can do here, this is kind of cheating, but kind of not. Since your square root of x squared plus y squared was, in fact, your z, I'm going to substitute a z in that spot. Well, that seems kind of weird. I know, but you can do it. In fact, the book solutions do it also. You don't have to. It'll still work out where you don't do it. But it'll come out a little nicer. And I'm going to do a similar thing with the partial with respect to y. The denominator is square root of x squared plus y squared, which is z. You're like, oh, okay. So now my surface area of the cone, and this isn't even the average value I'm doing yet, is going to be, 0 to 2 pi, 0 to 2. And I'm sort of kind of converting to polar at the same time. I'm not. So you're going to have 1 plus x over z squared plus y over z squared, like so, dA. But remember, z is square root of x squared plus y squared. So if you tried to clean up the radical, what's going to happen? And then rewrite this. And remember, this z squared is just x squared plus y squared. So if you
square root of 2, right?
Yeah, you're going to get, after you clean up this radical, you're going to, and then you add all the fractions together, because they all have the same denominator, then you'll notice that if you factor out a 2 after combining your like terms in the numerator, the x squared plus y squared cancels. Oh, man, after all that. Now, that's not the surface area, because you still have this double integral here. So that's, you're not done here. You just figured out what the radical is. You still have to do this. But then this double integral is the area of a circle. Is it? Yeah. Well, what circle? You know, pi r squared, where the radius is the projection of this cone onto the xy plane. And it's going to have a radius of 2. Oh my goodness. So the surface area of the cone is square root of 2 times pi times 2 squared, which is 4 square root of 2 pi. We're not even partially done with this problem. What do you mean? So the F average is going to be 1 over the surface area of the cone times the double integral of your fxy z ds, like this. Oh, now what? Ah, crap. You're going to put your 100 minus 25z in there, whatever they gave you for the F. Now remember, this ds is the surface area element. So what is that? And that involved that square root of 2 thing. So that was like square root of 2 dA. And then you can take this square root of 2 and move it in front because it's just a multiple. And then the z, you're not allowed to have a z in a double integral. Why not? Because double integrals technically are only supposed to be, you know, x's and y's, because that dA is dy dx. So then how do you even integrate this double integral? Well, z gets replaced by the cone. Really? Yeah. You think I'm making this up? No, I would not make this up. For real. So then what? Well, I don't feel like using trig sub. Like, this is going to be terrible. Well, yeah, I know. It's pretty gross. So this is where you're going to go, oh, like hell to the no. Am I going to do this? This is the part where you're going to convert to polar. Yeah, you're going to convert to polar. Like, no way you're going to do that. And remember that the cone, the region of integration is the projection of the cone onto the xy plane, where r went from 0 to 2, theta went from 0 to 2 pi. This integrand is 100 minus 25 r, dA, be a pirate, r, dr d theta. And then don't forget to distribute this r before integrating with respect to r. And I'll just say the final answer that I got after this integral ended up being like 800 pi thirds or something like that. Anyway, and so the final answer ended up being 200 thirds was the average value of that function on the surface area of a cone. Pretty hardcore. A lot of stuff involved. Okay, so it's kind of a scary problem, but it does involve a lot of knowledge of surface area, which is kind of why I like it. It's kind of like a double whammy kind of problem. Will we have something like that in the future? Yes, when we do the rest of 17.6, which is coming up in a couple weeks. Okay, but that concludes today's lecture. Congratulations. You now have all the material to do your exam 3.